Good afternoon, sirs and madams. Firstly, I would like to thank the St. John's team for inviting me to give this talk. I only have about 7 minutes to, it's a vast and engaging topic, but I'll keep it short. I'll briefly introduce Indrones and I'll give an overview of the ingredients that it requires to make a drone swarm, set the context of the in which the proposed solution that I'm going to talk about will get the most impact, and then talk about some of the work my team and I have done over the years, which puts us in a strong position to be able to tackle this complex problem. To the best of my knowledge, there's no off-the-shelf solution available in this category. So at Indrones, we've been building autonomous cyber-physical systems. That is, we are not just building hardware to serve different kinds of missions, but a software suite which enables the hardware to not just execute these missions in a most effective way, but to manage end-to-end drone operations. So we've been operating our drones for over a decade now across all parts of the country, and we've flown over tens of thousands of kilometers, have covered thousands and thousands of hours of flight, and completed about 150 projects and delivered to different enterprise customers across 10 different business verticals. So we've decided to extend these efforts to the defense use case also about a couple of years ago. So now to the main agenda. What does it really take to achieve swarming? You can easily see it in nature, but the primary ingredient that is required is the aerial vehicle to do the job. Depending on the type of mission, there can be different class of UAVs that can be used to do the job. There can be different configurations of these UAVs to serve the mission objective. Then the requirements of control laws or the algorithms to govern this swarming behavior. Then it is essential that each of these drones communicate with each other. A robust communication and sensing ability needs to be present on each of these drones. And then thirdly, it is important that these agents or these swarms react to the changes in the environment. This bit is what truly enables the swarm or the team to be more than the sum of its parts. So what are we up against? The recent conflicts have shown that there are different kinds of threats. Traditional air defense systems have shown efficacy against large UAVs. However, the high acquisition, upgradation, and operational cost of these systems is worth noting. The most menacing threat, what I feel among these, is the small UAVs that you can see on the top left. As they cost very little and they're easier to put together and swarm to use as a swarm against opponents. The use of larger and expensive counter UAV systems to guard against small UAVs in a way is a strategic win for the opponent because it bleeds resources during war. So what I propose, it is of utmost importance to restore the symmetry in an asymmetrical war front. The solution that I feel is swarms against swarms. So I'll first introduce some of the swarming capabilities that we've developed over the years and demonstrated over 5 years ago now. And as active users, some of you who remain seated, it might be of interest to understand how they can be used in current mission scenarios. And then I'll explain the swarm versus swarm bit after that, explain the kill chain in which this will play out. So we started working on swarm systems at IIT Bombay back in 2014, and by 2015 we developed India's first multi-copter swarm testbed from the ground up. We demonstrated decentralized control of different agents, which means that once you delegate authority to these agents, they can take decisions amongst themselves without needing to be connected to a centralized entity. Figure 1 shows 6 UAVs that can achieve rendezvous, that is meeting at a single point. Figure B shows the development of customized communication protocols to enable such behavior, which enables timely dissemination of information between agents. We also studied the issues that arise when there is a degraded communication between these agents, and how the behaviors of drones degrade if communication is hampered, which happens in EW scenarios. We've also demonstrated formation flight, wherein there's one human and other agents can autonomously follow in a formation. We've also in figure E, you can see how two UAVs can resolve a potential collision, and one stops and the other can go around and successfully complete the mission. Using all these primitives, we've utilized these algorithms to start building systems that can allow complete missions to be executed. In figure A, you can see three UAVs which are performing an area survey. Each vehicle is given different areas to surveil, and they can do the job independently. This is an example of a search and destroy kind of a mission, wherein UAVs take off from a home location, then they ingress into the enemy territory. Let me just speed this up a bit. So you can see that they have reached the target location, and they have onboard intelligence which enable them to take decisions on the fly, localize targets of interest, and once any target, they are now seen to execute a search pattern which is optimal in nature to find the object of interest, and then deploy a payload in case of any action that needs to be taken, and then egress back to the home location. This is something that we demonstrated back in 2020. So now let us visualize a scenario in which the opponent unleashes tens or hundreds of drones, small UAVs. The attack can either be pulse, mass, or maneuver against a defense system from various directions to achieve the objective of overwhelming the defense. This standoff distance would be in the tens of hundreds of kilometers. When the attack progresses and reaches the tens of kilometers kind of a range, we can utilize cheap vision-based and radar-based systems which come into play and allow the detection phase to kick in. Then the defender UAVs can take off to the sky and ready themselves for attack. They will have onboard localization and tracking capabilities based on which, once engaged with the target, they can pursue this target and then engage once their confidence threshold is above a certain point. The advantage of this kind of system is the feedback nature. You don't lose drones in such kind of maneuvers. You can recover them if the success criteria or the success is not met, and retry. So we put all these ingredients together to enable such kill chains. We've developed ground-based long-range detection tracking systems using EO and IR, demonstrated onboard tracking, of detection and tracking of small and large birds. We are also working with partners who develop radars to perform multi-sensor fusion and increase our probability of detection and tracking. We are also developing algorithms which enable swarms to take on other swarms. What you see in figures A and B is encirclement, wherein there is an evader drone which is in the center, which is engulfed by the pursuer drones, three other pursuer drones. And then we have mathematical guarantees that these drones, irrespective of the manner in which the evader attacks, will still be able to capture the evader. And we've graduated from doing this in 2D to 3D, and preliminary simulated trials at least show success in the kind of algorithms. We're moving that to actual systems. So the the engineering, like you saw, is the easy bit. What is expected from all the stakeholders in this room is to do a detailed threat analysis, create actual mission scenarios in which this needs to be implemented, determine the success criteria for which these systems can be built and qualified, and planning actually the trials for these kind of systems. Some trials have recently concluded. The feedback is that they can still be more well thought out, and actual mission scenarios can be recreated. These are newer systems that have not yet been developed. These need to be carefully understood and designed, and creating avenues to execute all these above. I think Professor Abhishek touched upon all the issues that can be tackled. So I won't add to that. So this is a combined effort across industry and academia that has been evolving over the last 10 odd years. And thanks for the time to talk about this. I work on this actively. Open office hours between 5 p.m. and 5:45 p.m. every Tuesday and Thursday to discuss anything about UAVs. You can book an appointment online, and I'd be happy to talk about it. Thanks.